Hello, my dear students, and welcome to a new chapter and a new lecture with our measurement course. In the previous chapter, chapter number 1, we have demonstrated together the main measurement concepts, how we can do measurements, different measurements type, different measurement scales, and even in the second half of this lecture, we have introduced the types of error, either a systematic or a random error, how we can demonstrate error in absolute or in a relative way, the difference between precision and accuracy, and how we can calculate the variation in the measurement or in the measured values. Today, in this lecture, we are going to continue with a new topic, which is still in our route toward the main theme of our course, which is the digital to analog converters, sorry, the analog to digital converters. Today, we are going to introduce the first and maybe the relatively more traditional way of doing measurements, which is analog measurements. Although nowadays it's rarely happen to use analog devices in doing measurements, especially what we are going to consider in this lecture, considering the analog voltmeter, analog ammeters, and analog ohmmeters or resistance meter. However, the concept beyond doing these measurements, or the concept beyond understanding these techniques is very important to mimic in different measuring techniques, even if these techniques itself are not widely used nowadays. So today we are going to tackle in this video the first half of the second chapter related to the analog voltage and current measurements. In the second video, in the second half of chapter 2, we are going to go to the analog oscilloscopes, which are still around. We can see in our labs still some analog oscilloscopes, and it's also important to know more about these analog oscilloscopes. So let's now start our journey. So as I mentioned today, our topic is analog measurements, how we do analog measurements. So traditionally or historically, the first way to do, or this first technique to do analog measurements was related to measuring the current. And this may be somehow related to some electromagnetic historical reason. So current, okay, so before going into this, let's start with introducing that this you can find in chapter 3 in our reference, Electronics, Instrumentation and Measurements by Bell. And of course, we have some additional helping materials related or coming from MIT Open Courses and UC Berkeley and some other useful links. You will find these all useful links in the e-learning page whenever needed. Okay, so historically, as I mentioned, the first way to do analog measurements was related to measuring current. And this was simply due to electromagnetic theories. I believe that most of you know this theory. When you have a magnet and when you have a coil, there is always a proportionality between the motion of the coil between the magnet and the current flowing in the coil. So maybe the concepts of the generators, for example, to give a mechanical energy in a form of a motion, and this mechanical energy is transferred into electrical current. And the reverse process happen when you study motors. So in motors, you give the motor electrical current, and this electrical current is turned to be a rotational motion of the coil inside the magnet. So in this way, the concept of the ammeter has been introduced. So as you can see here, we have a pointer here. This is a pointer, and we have a moving coil. This moving coil is between two magnets. We have a spring, and we have a scale. This is the major scale, and this is the minor scale. So simply the concept is, whenever there is a current flowing in this coil, this current will introduce an electromagnetic field, or sorry, will use the electromagnetic field due to the magnet in order to move the coil, and then the movement of the coil, which is here reflected in the spring, reflected in the coil between the magnet, this movement will lead to a motion for the pointer till it reach a value. Once the current stops to move, the spring will return back the pointer to the zero scale. So this is simply the process, how it is demonstrated, starting from a 0-point scale, which is the default value of the spring. Whenever there is a current and there is a magnetic field, then the pointer will start to move. The higher the current, the higher the deflection of the pointer, till it reaches what we call the full scale, which is simply the maximum current that can be conducted or passed through our coil, which represents the full scale range of this ammeter. This is simply the traditional way how people, maybe 100 years ago, introduced the ammeters. But herein, if we return back to this schematic, when we insert the ammeter in series in our circuit, where we have the voltage source and the resistance, we will find a very challenging obstacle, which is the maximum current that can be measured here by this ammeter using this concept is simply, is simply related to the maximum current that can flow inside the coil, which I just introduced here as the full scale range. Usually, the current that moved in the coil is not so large, or in other ways, it's always capped with a certain value. But in principle, we need to have our ammeters with variable scales. So we need to measure current in a milliampere, in a microampere, in ampere, sometimes in tens of ampere, and so on. How we can make our ammeter with a variable scale? So whenever you have a multimeter and you have the knob of the multimeter, you find that, for example, you can measure current in a microampere, you can measure current in milliampere, you can measure current in ampere. How we can change this scale of our ammeters? So the idea is very simple. The idea is mainly related of adding what we call a shunt resistance. So let's consider this example. Herein, for example, we have a coil. This is the coil, and the maximum current that can flow in the coil is 1 milliampere. The equivalent resistance of the coil is 50 ohms. So herein, a 50 ohm coil, this is the equivalent resistance of the coil, with a maximum current of 1 milliampere. That's automatically lead to that the maximum current that can be measured by this ammeter is simply 1 milliampere, which is the maximum current that the coil can resist. What if I need to double this range? So I need to make this current, this ammeter works with a full scale range of 2 milliampere instead of a full scale range of 1 milliampere. The idea is very simple. Let's put here a resistance in parallel with another 50 ohm value. So now, if you have a current of 2 milliampere, which is your targeted full scale range, this 2 milliampere once reach this node, it will find that we have a two parallel branches, both branches of the same resistance of 50 ohm. Typically, what happens that the current will be divided. 1 milliampere will go to the coil, and another 1 milliampere will go to the shunt resistance. Herein, the deflection will be proportional to the 1 milliampere you introduce. So, for example, if the current here is 1.8 milliampere, so 0.8 will move here, and 0.8 will move here. 0.8 means here 80% of the full scale range. Now, the full scale range is 2 milliampere. So what you are going to read on this scale is 1.6 milliampere, which is 80% of the full scale range. So simply, you can extend the range of your ammeter by simply adding a shunt resistance equivalent to the value you target for the full scale range. We can determine this with equation in a very simple manner. Here, Vm is the voltage on the meter, so which is simply the multiplication of 1 milliampere times 50 ohms. So here, 1 milli times 50 ohm, it will end up with 50 millivolt. This is the maximum voltage drop on our coil, on our meter. So Vm is, as I just mentioned, Im times Rm. Now you are seeking I total. What is I total? I total is the total current you are targeted to be measured. I total will be branched. Some of I total will move to the coil, which we call it Im, and this is restricted. This is capped value. And the remaining should move in the shunt resistance. So simply I shunt is the subtraction of I total minus Im. From this equation, you can determine the value of the current you target to pass through your shunt resistance. Now you know the current that should pass through the shunt resistance, which is Is. And definitely you know the voltage across the shunt resistance because it is a parallel branch. So it's typically the same voltage as the voltage on the meter. So simply the shunt resistance you are going to add should equals to the voltage drop on the meter, which is Vm, over the current expected to pass on the shunt resistance, which is Is. And from this equation, you can simply calculate the value of the R shunt or the shunt resistance. So as you can see here, for 50 millimeter voltage, and the R shunt was 1 milliampere, as you can see here, we typically need a 50 ohm resistance, which is the example we just do together in order to double the range of our ammeter. So this is typically how we can extend the range of an ammeter. Let's have another example here in the same direction. So as you can see here, we have, this is again a restricted value because this is simply the coil. So you are not going to change the coil. This is the fixed ammeter coil. Here the coil is with 1 milliampere voltage and 1 milliampere current and still for 50 ohm resistance. So again, the voltage drop here will be 0.05, which is 50 millivolt. Now, your target, my dear students, is to extend this scale 5 times. So instead of measuring 1 milliampere, you are seeking to measure 5 milliampere, which is 5 times the full scale range of your coil. Simply in this case, what you are searching for is that you are searching for a new resistance, a new shunt resistance to be inserted in parallel to the coil so that the new shunt resistance should have 4 milliampere moving. Now, the expected current to move in the shunt resistance is 4 milliampere. The expected voltage is 50 millivolt. Simply, the resistance you are searching for is Rs, which is 50 millivolt over 4 milliampere, which will end up to 12.5 ohm. So if you add a 12.5 ohm resistance, that's 5 times increase your full scale range. And this is another example. But you have to consider a very important effect, which we call the loading effect. What is the loading effect? Let's see. Okay, so here, my dear students, when you go to this circuit, for example, let's go to, this circuit, for example, here. In this circuit, if I told you, my dear student, please calculate the current flowing in this circuit, what you are going to say, oh, it's very simple. We have a voltage source and we have a resistance. So the current flowing here is simply I equal V over R. If you have the V, if you have R, you can simply calculate I. So it's straightforward like that. And in principle, this current should be the same regardless the tool you are using. So regardless the type of ammeter you insert in the circuit, you should get the same value. So for example, if here we have a resistance of 10K, and here we have, for example, 1 voltage, 1 voltmeter source, then the current should be 1/10, which is 0.1 milliampere, regardless the type of the ammeter you insert in series. But what happened is not as expected. Let's describe it to you. If you use the first ammeter, which is this one, this ammeter includes a coil of equivalent resistance 50 ohm, and you add another shunt resistance in parallel, which is another 50 ohm. So the overall resistance of this coil, of this ammeter, is 50 ohm parallel with 50 ohm, which is around 25 ohm. So in this case, if you insert this ammeter in this circuit, the equivalent ammeter resistance is 25 ohm. So in this case, if you are considering the current here, the current will be V over this resistance R plus 25 ohms. But if another colleague uses a different ammeter with a higher scale range, and he uses this configuration, so in this case, we have 50 ohm parallel with 12.5 ohm. So the equivalent will be around 20, maybe relatively less than 12.5. Let's say it's 10 ohm. So now the equivalent resistance of the ammeter is 10 ohm. So if you insert this ammeter to the same circuit, the overall resistance seen by the supply will be R plus 10 ohm, which will reflect on the measurements, because in the first case, we have R plus 25 ohm, while in the second case, we have R plus 10 ohm. You can tell me, oh yeah, you are right. However, if this value is 10K, then it doesn't matter, because in both cases, 10K is much greater than either 25 ohm or 10 ohm. You are right. But if the value here is 100 ohm, then in one case, it will become 125 ohms, and in another case, it becomes 110 ohms. If the value here is 10 ohms, so in one case, it will be 35 ohm, and in the second case will be 20 ohm. We have two bad news here, my dear students. The first bad news is, but while changing the measuring system, the ammeter type, we change the reading, because one have an equivalent resistance of 25 ohm, and the second is having an equivalent resistance of 10 ohm. The second big news is both readings are wrong, because ideally, when you put an ammeter here, you assume that this ammeter is with a zero resistance. But as you see, in both cases, one time it's 25 ohm, which is not zero, and in the second time, it's 10 ohm, which is again not zero. So this is very important, and this is what we call the loading effect. So whenever you are using an ammeter, you have to consider this loading effect in your measurements. Okay, let's go to the second part of our story, the second important parameter to be measured, which is the voltmeter. Generally, one of you can tell me that, okay, we can use the same concept in order to measure voltage, because as we definitely know, voltage and current are proportional. V equals I times R. So the higher the current, the higher the voltage. And using again the concept of the deflecting pointer, you can you can measure the voltage as well as you can measure the current, which is, of course, typically correct. So if we go to proceed with the same process or with the same procedure in order to measure the voltage, what we are going to do simply, my dear students, is we are going to put a proportional scale to the voltage equivalent to the current, because simply we know that Vm equals Im times Rm. But again, facing the same problem we faced with the ammeter is that the coil have a limitation. It has a limitation in terms of current, which will equivalent to a limitation in terms of voltage. So applying the same concept, if we assume that we have Im times Rm equal 0.1 voltage, for example, this is the example. So the maximum voltage that you can measure is simply 0.1 voltage, which is still too small. In many times, you need to measure voltage greater than 0.1 in the milli range, hundreds of milli range, or even the voltage range, tens or hundreds of voltage. Now, if you add a resistance in series, this resistance in series will not impact the voltage. If you add the resistance in parallel, which is the same as in the previous example, this resistance will not impact the voltage. It simply impacts the current. Because as you know, when you add the resistance in parallel, the current is branching, so you maximize the current because you have a current flowing in the meter and I have a current flowing in the shunt resistance. So a parallel or a shunt resistance model here will not work because you don't want to increase the current. You need to increase the voltage. So what will happen here, my dear students, is that you are going to add a resistance in series. Because if you add a resistance here in series, the overall voltage across your meter will be the voltage on the meter itself, or the voltage on the coil, which is Vm, as we mentioned here, or the same terminology we are using here, plus the voltage drop on the added series resistance, which is Im still times Rs, which is the series resistance you add. So in order to know the value of this series resistance, you need to understand how much voltage you need to measure. So for example, now your coil can measure 0.1 voltage, and you need to extend this range to 25 voltage. So you need an additional voltage drop of 24.9 voltage, so that the overall voltage range is 25. So in order to add it, it's very simple. You are going, okay, so I need a voltage of 24.9, and I need resistance. Let's say, for example, that the current flowing is, for example, 1 milliampere. So in this case, that's very easy. That the resistance I need is the full scale range voltage I need, which is 24.9, over the resistance is the current value, because it's the current in series here. So 1 milliampere. So simply it is 24.9 kilo ohm. So you need to add a resistance in series to be 24.9 kilo ohm. This resistance will make the overall voltage drop across this multimeter, or across this voltmeter, to be 25 voltage in a very simple manner. But now, if your device have an overall resistance of around 24.9, which let's say 25 kilo ohm, is it possible, or is it logic to make this device connected in series? If you connect this device in series, you will definitely impact the reading. It's a very huge resistance of 25 kilo ohm. So adding this in series will impact the value of your reading. So the action that we can do here, my dear students, is that to connect the multimeter in parallel. Because simply, if you connect the multimeter in parallel, what will happen is that you will sacrifice minimum current because your resistance is relatively high. But again, let's discuss the loading effect. Before going into the loading effect, let's see this schematic. So this is your meter, and these are the resistance you are connecting in series. So if you go to your multimeter now and see the knob in your multimeter, you will find that we have different scales. For example, starting from a micro voltage range, a millivoltage range, a voltage range. So you can simply change here by changing the value of the series resistance added to your multimeter. The higher the value of the series resistance, the higher the overall voltage range you are measuring. So because simply you add more drops. So for example, between these two terminals, the voltage drop is simply this voltage drop on the meter, which is constant, plus the voltage drop here on the 48K. If you go to this selector, then you have 3 voltage drop. You have this one, and this one. So the higher the series resistance you pick up to your meter, the higher full range you got for your voltage source. Going here back to this important point related to the loading effect. Now, if you see this example, now let's say that this is the ideal circuit, which is circuit number A. In this ideal circuit, we have 120 voltage connected across two resistance. The first resistance is 60 volt, is 100 ohm, and the second resistance is 100K ohm. So they are two identical resistors. And I want to measure the current between these 2 points, between point number 1 and point number 2. If you see here, my dear students, and based on the circuit theory we know, and based on the potential divider theory, the voltage drop on this resistance R2 should be typically equal 60 volt because we have two identical resistance. So the voltage drop here should be the same in both resistance. So this 120 is divided into 60 voltage here and 60 voltage there. Okay, that's great. Now we need to verify this experimentally. So we go here and we bought a voltmeter and we connect the voltmeter in parallel as we already described. And let's assume that this voltmeter has an internal resistance of 100K. So what happens simply, my dear students, that this resistance will be impacted by the 100K because now the voltmeters, the voltage source C, 100K, then these 200Ks are as if they are connected in parallel. And based on the circuit theory we know, these 200Ks connected in parallel is seen as a two parallel resistance of an equivalent of 50K. So from the source point of view, we have 100K connected with 50K. So the voltage divider process here is not symmetric. It's not 100K to 100K. It's 100K to 50K. So the voltmeter reading will be 40 volts, not 60, which is a deviated wrong measurement, simply due to what we already mentioned in the ammeter, which is the loading effect. So how we can minimize the loading effect? If you remember my previous chapter, the bad news slide, I told you that in all cases we have error. The idea is simply how to minimize this error. So whenever you are doing a measurement with a voltmeter or an ammeter, you are impacting the circuit and you are deviating from the correct, or what we call the conventional true values, the CTV. The idea is simply to what extent you are deviating. So you are acting only to minimize the deviation factor. How we can minimize the error here? The answer is very simple. The problem occurs simply because the resistance here, which is the internal resistance of your voltmeter, is comparable to the resistance here, which is the 100K ohm available in your circuit. What, of course, you are not allowed to change this resistance, because this is simply the resistance in the circuit. But what we can do is to increase the internal resistance of your voltmeter. If you increase the internal resistance, because again, you are controlling this resistance by adding these values. So you are the designer of the voltmeter. You can increase the resistance of your voltmeter. You can do so. So what you can do simply, my dear students, is to go with a very high resistance. Let's say in the mega ohm range. So principally, there is still an error, because now 100K ohm parallel with 10 mega ohm is not 100K. It's slightly less than 100K, but it's slightly less. So the deviation error here is nearly neglectable with respect to the conventional true value or the exact value. So what we did here simply is that we go with a very high available value for the internal resistance of your voltmeter to minimize its loading effect. But one of you can simply tell me a very tricky question. What if the resistance in my circuit in principle is in the mega ohm range? So definitely here, the range of error will increase. Again, there is always an error. The matter is that we are trying to control and minimize this error. In the same direction, we can think about the ammeter if we return back to the ammeter slide. So we can think in the same way with the ammeter. As you see here, whenever I decrease the value of this resistance, this shunt resistance, whenever I decrease its value, I minimize the overall resistance value of the ammeter, and accordingly, I minimize the overall impact of the noise, of the error, because simply, as you can see here, you are adding the resistance in series. So whenever you are adding the resistance in series, you need, or ideally, you are seeking a zero resistance. So if you are seeking a zero resistance, the lower the resistance, equivalent resistance of your ammeter, the better the performance. And this is important as well. So a third interesting source, or not source, I'm sorry, a third interesting equipment or measuring system is the ohm meter or the resistance meter. And if you return back to my previous chapter, you will find the difference between the passive measurements and the active measurements. The first two measurements, I mean the voltmeter and the ammeters, are passive measurements, because simply we did not induce either a voltage or a current. We are just measuring the voltage or the current in the circuit. Now here, this is an active equipment, simply due to this 1.5 voltage source. So because simply you are measuring a passive element, which is a resistance, you need an internal exciter in your device, which is this 1.5 volt. The idea is very simple. You are now running current through this 1.5 voltage, and you add this coil as an ammeter in order to measure the deflection of the current moving. And as you already know, this resistance is used in order to extend the voltage range. So you now can estimate the current from this value, and you already know the voltage. Knowing the voltage and the current, you can calculate the value of the resistance. So here, you already know that you have an internal resistance of 1.5K, which is a very important point, that here the loading effect is minimum because we already do the active measurement, and this is one of the advantages of the active measurement. We know the internal resistance. We know that we have a 1.5K already in our source, in our meter, in our own meter. So what you are doing here is just you are going to substitute this total resistance from 1.5, and this will give you the true value of your resistance, because simply you know the value of your internal resistance and you know the value of the source. Okay, so simply you have one unknown in this equation, which is the resistance to be measured. And again, you can have the deflection here, but as you see, my dear students, and this is a very tricky point, by the way, that the scale here is not linear. It's not a linear scale, because simply you are dealing with an inverse process. So you are measuring current, and R is proportional to 1 over I. Simply R in the equation here, R equal V over I. V is constant, R is the value to be measured, R is the output value, and I is the value to be measured. So it is a reciprocal relation. You calculate I, and you know that R is 1 or V over I. That's why it ends up, instead of having a linear scale, it ends up to 1 over X scale in order to have this variation. Again, as I mentioned in the beginning of this lecture, most of these devices are now out of date and they are no longer used in this form. However, what we are seeking from this lecture is not the equipment, is not the measuring equipment, it's the measuring concept. How we are using coils, how we are using the resistance in order to measure voltage current resistance, and in order to vary the scale or vary the range of the measurements we are doing, where we are facing. This is the concept that will be beneficial for you to understand, rather than dealing with this traditional equipments, because as I mentioned, these are out of date equipments and they are no longer available. That's for today at the first half of chapter 2. In the second half of chapter 2, we are going to explore another interesting and relatively still in stock device, which is the oscilloscopes. How we plot an AC signal in an oscilloscope or a cathode ray oscilloscope. Thank you very much for your concentration, and see you in the second part.